You sit down, type out a prompt asking an AI to build a simple application, and hit enter. You expect it to map out the logic, conceptualize the project, and write clean code. Instead, you get a wall of broken text and hallucinations that fail to even compile. That breakdown happens because we assume the AI understands our goals the way a human coworker would. It doesn't plan. It doesn't conceptualize. It doesn't comprehend a single word you type. If you talk to it like a person, you guarantee your own failure. To get exactly what you want, you have to operate by the system's actual rules, and those rules are entirely mathematical. Under the hood, a large language model is a vast, multidimensional spatial coordinate system. It is a universe built completely out of linear algebra. When you submit a prompt, a process called tokenization kicks in. The model chops your human words into smaller pieces, assigning them numerical IDs. The phrase, "How are you?" becomes a raw array of numbers, like 23-4, 12, and 99. Next, those numerical IDs translate into dense vectors, plotting as exact coordinates on a 3D plane. Words with similar meanings, like cat and kitten, map extremely close together in this mathematical space. Something unrelated, like car, plots far away in a distinct cluster. Vague prompts launch a blind trajectory into this infinite space. The math flatlines. With millions of equally valid directions it could travel, the AI drifts aimlessly and produces hallucinatory garbage. To navigate this space, the model relies on its context window. Think of this as the active radar of your spacecraft. It loads every single word you just typed into its active memory. Inside that radar, the model uses an architecture called a transformer, which runs on a mechanism known as attention. Here, we see a web of vector lines connecting a sequence of words. This illustrates the attention mechanism calculating the mathematical gravity between every single term in your prompt. Notice how the connections between Python and calculator glow thicker and pulse. The system assigns heavier mathematical weight to these critical terms, using them to anchor its trajectory. The engine then fires up the autoregressive loop. The model does not calculate a whole application or essay at once. It travels one single word, one specific token at a time. Grasping what you want is strictly a calculation of the gravitational pull between the data points you provided. Look at this fluctuating bar chart showing probability percentages. The model runs billions of algebraic equations to calculate the probability distribution for every possible next word in its dictionary. One option spikes higher than the rest, representing the most likely next step. The system selects that highest probability word and appends it to your original prompt. That new, longer string of text is fed back into itself, and the math resets to calculate the next jump. When it generates a working calculator script, it isn't thinking about software architecture. In its mathematical space, the terms you prompted are heavily linked to specific syntax structures mapped out during training on millions of GitHub repositories. To keep these trajectories stable, engineers apply reinforcement learning from human feedback. This acts as the underlying laws of physics in this universe, shaping the natural gravity to always pull the model's outputs towards safe, helpful regions. Writing code or text is a relentless statistical replication of patterns. Avoiding chaotic space demands precise piloting from the user. Because language models are purely probability machines, your only job as a user is to restrict their mathematical choices. Assigning a specific persona or using retrieval-augmented generation to feed the AI specific documents is like uploading a custom star chart. It instantly limits the vocabulary and coordinates the model is allowed to access. This diagram illustrates the most effective control method, providing few-shot examples. Watch the scattered wave of data points collapsing into a single sharp spike when a specific constraint is introduced. Giving the model an exact example of the input-output format you want acts as a massive gravity assist. The attention mechanism heavily weights those examples, forcing its pattern matching to lock on. Applying rigid constraints removes the model's ability to guess. You mathematically spike the probability of the exact correct response you need. You can also control the model using chain-of-thought prompting, which establishes sequential navigational waypoints. Language models calculate their compute power on a strict per-token basis. Demanding a complex application instantly forces the model to guess the very first line of code without any architectural context. You are forcing it to make a blind jump into deep space. Here is how we fix that blind jump. Notice the first trajectory shattering into fragments when it attempts a massive leap. When the visual resets, the line connects sequentially through distinct, stable waypoints. By forcing the model to write out the architectural steps first, it generates stable, localized coordinates. It then uses those very steps as the mathematical context to write the final code. The text you see on your screen is just the localized exhaust of an immense, continuous cosmic calculation. Stop talking to these models like they are human collaborators and start piloting them like the mathematical spacecraft they actually are.